So before I start with all the cool announcements, I want to get a level set with where everyone's at. So raise your hand if you have worked with HDR textures before, or HDR anything. Yes, I love it. Okay, raise your hand if you have worked with compressed GPU textures. So that'd be like BC 1 through 5. A lot of folks. Okay, I'm so happy. So then you probably know this intro, but I didn't notice everyone raise their hand, so I'll kind of go over it just in case. We're Binomial. We've been in business for 8 years, and we specialize in GPU textures. So we specialize on keeping things nice and small on the GPU and cross-platform. That's the key, and that's really the innovation here, is that for the longest time, you had to store a copy of every single GPU texture to be cross-platform, and we really help you out there. We provide a solution. So this is kind of where we were at when we first released. We released in 2019, and then in 2021, when we introduced WebAssembly, transcoders, and things, it really started picking up on the web. You can see a photogrammetry example. The GPU size was 682 megs with JPEG and 85 with our technology. Massive savings on the GPU. You can see with JPEG, the download size is a little smaller. That's typically what you'd expect, but we were on par with usable comparisons between JPEG with the SDR model. And so you can see, we transcode actually to even more than this, but I didn't want to completely crowd the slide. With our SDR workflow, you just encode once to KTX using Basis Universal. And then in real time, you can transcode to any of the mobile formats, any of the desktop formats. It stays compressed on the GPU. And when I say real time, I mean it. It's on par with JPEG decompression, lossless decompression, things like that. You really won't notice it that bad. You just have to stick it in your pipeline where you would normally decompress and shove an uncompressed image on the GPU. So you can see another SDR codec example. This is between DXT. You can see, especially in immersive environments, this is in Play Canvas, you don't really notice the quality. Our HDR codec is even higher quality than this by far, but you can see there's not a massive quality difference, especially in environments. But there are major compression benefits. So you can see download size in blue and VRAM in red. Ours is slightly higher in this example because they're doing fancy normal map stuff. But yeah, you can see it's massive. Even compared to the legacy texture compression, even if you just had one DXT file, which would not be cross-platform, we're still smaller than that. So it was really innovative and still is. HDR, though, is the fancy announcement. So with HDR, just in case you didn't know, most of you did raise your hand, it's high dynamic range. So you can see with an SDR display, we don't have all this data. We could only really show one image. I'd probably pick the middle image to show you, and it's tone mapped. And you can't really see all the detail of the window, even though I tried my best to have the best balance between them. With an HDR image, you can get all this data in one image, and that's amazing. It's amazing for photo editing, for lighting pipelines, for all kinds of applications, to just be able to have the full range of light to use at your fingertips. And I really do believe that HDR hardware will become more and more widespread, so it won't just be about better data, better photo editing, things like that, but it'll also be about being able to be displayed on an HDR display. So with our HDR pipeline, it's a little different. There's not as many HDR formats, but there's still not a cross-platform HDR format. So we have UASTC for mobile HDR, some laptops, but mostly mobile, BC6H for desktops, and then we also give you the option to do half-flow uncompressed, because I know some HDR developers like to be fancy and do extra stuff on the GPU with uncompressed files. If you want that, we got it, and you can use us as a storage solution. That's totally fine. So we're going to get you 6x compression with this initial release. We may have more releases coming that get you even more compression than that, but 6 times compression on both the storage size and the GPU. And it's pretty cool. We're going to have WASM transcoding with this release, which was not true of our original release. And the quality is ridiculous. I couldn't show you that original HDR example because like it looked exactly the same as this. Like it would just be showing you two exactly the same images. So I tried my best to get really in there into the pixels to see if you can find any differences between the images. There are actually differences, but I bet you can't really perceive them. And it's mobile GPUs and desktop GPUs are the ones after, and then the original is the highest quality HDR version. So you can see, it's pretty cool. So we are going to be going in depth with this technology later today at 1 p.m. at the GLTF booth. We'll really talk about like how it is built and if you want to contribute to the spec. We build the spec in the 3D formats calls, but we wanted to present here because it has so many web applications. As you can see, most of you raised your hand when it came to this. But we'll give you a flavor, a little taste of it. Rich will go into some of the nitty-gritty of how it's built, and at the end, there are even more benchmark examples. So yeah, go for it, Rich.
Wow, this is a big audience, and much bigger than I expected. Thanks, Stephanie, really appreciate it. Okay, so I can't see my slides here, but I can see them there. Is that all right?
Okay, is that all right?
Yeah, that's fine. I can actually see this, so this is good. Yeah, so I'm a software engineer. I've been doing graphics programming since the early 90s. And I'm going to apologize to you up front for such detailed slides. I know they're very dense, but you know, Stephanie told me like, hey, you got to go to SIGGRAPH, you got to present, and we're shipping in 4 weeks. I'm like, oh shit. So here I am. Yeah, so I'm going to apologize. I'm not going to describe the high-level details of block compression much in this presentation. Instead, I'm going to just talk the nitty-gritty details, the battles that we face getting this tech out. So we've been working on this technology for about a year now. Basically, the tech that we're going to ship is based off ASTC, and that means adaptive scalable texture compression. It's super flexible. It's incredibly flexible. It's the most complicated GPU texture format. It's really engineered for GPUs, so GPUs can consume it very efficiently. It's fixed bit rate. It's not like JPEG where you can like, it doesn't have a variable bit rate across the image. Instead, the image is divided up into blocks, which can vary in size depending on your settings when you compress the texture. It's a fixed block size, and it's lossy. So it was developed, and this is important, like I realized while getting really deep into ASTC that the engineers who developed this at ARM and AMD, they were visionary. Like I'm blown away by what can be done with this format. And it's gotten a lot of heat because it is so complex. But you're gonna see in a second what we can do with it. So ASTC supports LDR and HDR, and Basic Universal already supports ASTC LDR. So when in HDR mode, it's half float or FP16 or an IEEE standard. AST supports different block sizes, 4x4 to 12x12. Note that when you encode a texture, the block size is fixed in stone. So if you select 4x4, you only get that block size, for all the blocks in the entire texture. Supports all kinds of features, upsampled weight grids, tons and tons and tons of features. It drives encoder authors crazy. Actually, there's really only, to be honest, there's only one encoder in the world that supports all of the features to my knowledge, and that's from ARM. Okay, and so on desktop, unfortunately, most desktop CPUs or GPUs don't support on ASTC. It's just too complicated. So instead, the good enough alternative for Microsoft is called BC6H. And BC6H has a bunch of constraints, such as only 4x4 block size, so it doesn't support the larger block sizes that ASTC has. It's always 8 bits per texel. However, BC6H supports unsigned and signed, while ASTC only supports unsigned. Okay, so the deal is this: like right now, there really are only a handful of solutions if you want to distribute HDR texture content to every GPU in the world. And the two major solutions I'm aware of are, first, you can just encode to both ASTC HDR and BC6H, and that's what some engines do. Like, I believe Unity does that today, for example. And the problem with this is you get two encodes, twice as many bugs, twice as many APIs, twice as much optimization effort on the encoder side, and you get 2 extra storage costs. And you get different artifacts too. So, from an art pipeline perspective, the artist would have to, perhaps look at both to figure out, okay, are these both usable? An alternative solution is to real-time encode on the target, which has its own problems. So that requires extra power, complexity, potential bugs due to driver interactions, pipeline bubbles, everything's trade-offs, and so there's different trade-offs with this. But one of the biggest trade-offs is you're going to lose quality for that. Okay, and so I just wanted to mention too that the compressed GPU texture formats are the black sheep of the image texture compression approaches. There's very few people in the world that work on this stuff. Okay, so this is UAST HDR. So what we're going to do is we've decided we're looking at the entire ASTC HDR spec and LDR, and we're like, okay, we're just going to whittle this down to the things that give us the biggest bang for our buck and are compatible with BC6H. Anything else, we're just trimming away, and we're trying to compensate with a smarter encoder. So we're naming this UASTC HDR. We've already shipped UASTC LDR, or at least one variant of that, and that supports all the LDR formats. And so what we're going to do is we're going to leverage all of the knowledge and infrastructure that everybody has with ASTC, and just kind of piggyback that and say, okay, well, we're going to get rid of a whole bunch of features. You're only allowed to use this stuff, and this is the subset that can be transcoded efficiently, and I'll explain what that means in a second, to BC6H. So some of the constraints are, it's always 4x4 block size, always 8 bits per texel. The input to the encoder is always 48 bits per pixel. There's no alpha, and the reason why is because BC6H does not support alpha. It supports, in terms of features, and I'll get to that in a second, it supports all the major features that I think we need to ship a codec that doesn't have horrible block artifacts. So it supports solid color blocks, which are lossless, lossy one subset, 2 subsets with 27 common partition patterns out of 32 possible BC6H. So how this, really fast, how this technology works is it divides up, and I'll show you some images in a little bit, divides up the texture or image into 4x4 blocks, and for every block, it analyzes the block, and it tries a whole bunch of different ways of encoding that block. So it could try a solid color block, like all the texts are the same color. It could try, it could choose 2 points in HDR color space, and then assign to every texel a color along that line in color space. So that's one subset. Or it can assign that block 2 color space lines, and it can control on a block-by-block basis which texels are assigned to each line. So BC6H only supports 2 lines, so that's what we're limited to here. And so the key thing is this. UASTC HDR data is ASTC data. So there is no transcoding, there's no extra step involved for deploying UASTC HDR content on mobile devices. So you can just give a pointer to the driver or the API, the UASTC data, and everybody's happy because it's actually just ASTC data. However, if you're on desktop, we have to transcode or convert from one compressed format to another right on the device, on the CPU. However, it can be done in compute as well. So, and the way this is done is we unpack the high-level block configuration, the ASTC block configuration. We go from the physical to the logical level. Once we have the block configuration, and that consists of basically the color space lines, coordinates in 3D space, and for every texel, an integer index from 0 to 3 or up to 0 to 15, where along that line each texel color lands basically. And so we quickly just unwrap that from the ASTC data, and then we rewrap it up in a BC6H's encoding. And believe me, this is mind-numbingly complicated. It's insane. So that's why it's taken us a year to get here. Especially BC6H is quite sane, but ASTC is you just pull your hair out. It's incredible they're able to squeeze all these features and actually ship it on hardware with ASTC. So the key thing is this, is that we don't decompress the texels. We don't have to recompress each block. We don't have to do a search to find, where the lines are at in color space, because that's already been done for ASTC. Okay, so the deal is ASTC to BC6H is typically lossy. However, the loss is amazingly tiny. I'm going to be honest, I didn't know this was possible. I'm surprised that we're able to do this at all. It's one of the fraction of a dB. It's almost impossible visually to see the difference. Okay, so I'm just going to be upfront. These are the slides that make Stephanie, my business partner, uncomfortable. Okay, she's like, can you just go through these really fast? And all right, so these pros and cons and risks, especially the risk. She's like, no, don't go to the risk. So everything's about trade-offs, right? And so I'm just being upfront. Here's where our trade-offs are, and I'll have some graphs in a second. So here's the deal. The pros are it's just ASTC, so everybody's already familiar with that. Our encoder is an ASTC encoder. However, unlike ARM's encoder, it's a dual format encoder, meaning we're encoding simultaneously to ASTC and BC6H. So we have all those complexities wrapped in one encoder. We can leverage the existing spec, which is quite large and well developed. It's simpler than targeting full ASTC HDR. So if you wanted to write your first ASTC encoder for fun, you're a real masochist and you really want to go there, you can actually target this first, and you can learn a lot before you go to the full ASTC spec. So there's no transcoding on mobile devices. So I just want to note that it is possible to encode to BC6H and transcode to ASTC, so the opposite approach. However, then all the mobile devices which are power constrained would then face a transcoding cost. So we decided, no, we're going to go to ASTC because all that's mobile hardware supports that, so there's no cost on mobile, and we only have to pay the actual transcoding cost on desktop. The other cool thing is that we can improve the encoder over time. So this encoder is not locked in stone. However, the constrained format of ASTC will be locked in stone in the spec. So here's the cons. Obviously, it's going to be lower quality. We're removing ASTC features. It doesn't support alpha, which we could not squeeze it in there, but BC6H does not support alpha. So if we did support alpha, we would actually have to hand you two textures. So maybe in a future version we can get alpha in there. ASTC HDR alpha does sacrifice quality. That's another reason why we're like, well, let's just work on RGB for now. No signed values. I don't really think that's a big deal. And our reference encoder, ARM has done an amazing job optimizing their encoder. It's like just for such a complicated format, it's amazing like how fast it is. Right now, we're working on a reference encoder. So one of the things I wanted to mention is that because we're just constrained ASTC, anybody with an existing ASTC encoder could support this. Okay, here's the risk. This is the slide Stephanie doesn't want people to say. Okay, here's the risk. So when we're doing this, we're looking for outlier blocks. So most blocks, frankly, are very simple to handle. It's the blocks that have a lot of edges, a lot of Keller transitions. Yeah, those are the nightmare blocks. And invariably, somebody out there is going to give us a bug and say, my blocks, my image doesn't look right. And I'm like, oh boy. So outlier blocks are really what we focus on. And as we push and get the quality of the codec up, we're dealing with more and more outlier blocks, honestly. So we have a massive library of outlier blocks that we've been building to try to work on this. So the deal is, I'm not worried about ASTC or UASTC HDR on mobile. The main worry I have as a codec author is making sure that the transcoded version on desktop looks, it should look virtually identical, if not identical. There are some outlier blocks that I'm personally not happy with. However, I think the vast majority of people wouldn't even notice them. So the other thing that's a risk is once we have a spec, it's locked in stone. And so what do we want to lock in stone? What do we don't want to lock in stone? So what I think we're going to do this time, in our previous formats, we locked everything in stone. So we basically said, this is exactly how you transcode to this format, and this format, and that's it. And the reason why is because the encoder was basically doing all those transcoding operations during encode time and figuring out what the error would be. And this time we're going to do it a little differently, and I'll show you why in a second. We're only going to give you a recommendation on how the transcoding should occur, because then we can improve it and others can improve it as well. Okay, and so the other risk is that the subset that we have chosen is not strong enough for everybody. I'm not very worried about this. We've chosen a very strong subset. Okay, so this is the nitty-gritty. I'll go through these really fast. These are the exact features that we're supporting and will be spec'd out. We're going to support solid color blocks, Keller endpoint mode 7 in ASTC, which are Luma lines in HDR color space with 1 or 2 partitions, SEM 11, which is arbitrary lines in HDR color space, 1 or 2 partitions. And for these SEMs, this is AST terminology, we're supporting all of the submodes. So this format has modes and submodes, and it's really fun. So anyway, we're supporting different ways of encoding quantizing the endpoints. That's what ISC basically means. And we're supporting different ways of quantizing the weights. Most importantly, we're supporting 2 partitions. So BC6H supports 32 different ways of figuring out, which textiles assigned to which color space line. So we're able to support 27 of them. These are the ones in common between BC6H and ASTC. So weight grid must always be 4x4, so we're not going to support upsampling. I just don't think it's necessary, though we have prototyped that. Anything else in the ASTC spec, which is a chrono spec, by the way, is not UASTC HDR. So no dual plane, no other SEMs. Okay, so real fast, the transcoder is a full-feature transcoder. It supports all of the modes that BC6H supports. The transcoder has to have really, really simple search to figure out, okay, which mode do I want? The weight, and most importantly for performance, the per pixel texels are just translating using really simple 1D lookup tables. So there's nothing fancy going on there, and it's just like a one-to-one mapping. And so the encoder does, with that color space line thing I was talking about earlier, the way the interpolation occurs between the formats is slightly different, unfortunately, and the interpolation weights are slightly different, and the encoder does its best to work around that during encode time. Okay, so I'm going to skip some slides you can always read later just for time and get to the images. Okay, so I'm basically talking about quality metrics, which I'm constantly struggling with, is how to find a quality metric everybody can agree on. So, okay, so here's these are some, I just kept it really simple. 6 different images, or 7, sorry. And these are common HDR images you can find on the web. I've encoded these images with our encoder and ARM's ASTC Inc. Latest version I could find on the web with its thorough options. It's the maximum quality it's able to achieve. The higher the bar, the higher the quality. This is a logarithmic quality metric. Anything above approximately 45, I'm happy with. So, and I just chose a bunch of images really fast. On the right, we have Sponza, which is really tough for us to handle. It's an artificial image. I think it's like ray traced or photon mapped or something. We're able to get around 45 for that. So there's some key takeaways from this slide here. First of all, UAST HDR in orange and UAST HDR to BC6H in green, notice they are virtually identical. Now, what I don't show in this slide is it is actually possible for BC6H to be higher quality, which is, to me, kind of mind-blowing because it's an ASTC encoder. So we're going through ASTC to get to BC6H, and we're actually able to get higher quality that way with BC6H sometimes. And you can see that that's the key thing here, is we want to make sure that the quality is predictable across the 2 different formats. Depending on the image, you're going to get almost the same quality, or depending on the image, you're going to get a loss in quality. However, the loss seems to be around 5 to 15 dB. The quality is already really high and hard to see the differences. And so we got a bunch of feedback, and we've given these slides. And everybody's like, well, where's your images at? And I'm like, well, wait a second. If I just showed you zoomed out images, you wouldn't see anything, because this is an LDR display. It's probably going to be JPEG'd, it's in slides. So we're just going to zoom in. And you can see here, this is actually a really hard image. This is Sponza, the one that got the worst compression artifacts. And I know where these artifacts are at. I can see them. But these, if you look here, these are the 4x4 blocks. So every block is encoded independently in this format. Left is the source, UAST HDR, which is just ASTC, is in the middle. And then the transcoded version is at the right. And they're virtually identical. And by the way, this is an HDR image, and unfortunately, we have an LDR display going through, slides. So we had to tone map this to even display it, and it's a very simple Reinhardt tone mapper, one of the older ones. Okay, so another image. We already showed this earlier. Let me get to another image here. So what I'm going to show here real fast is this is tree.exr, has extremely high dynamic range. I just chose a harder part for us to handle. We have a contrast here between a sky and the tree, and the codec has to deal with that massive transition of dynamic range. And so this is the source. This is UASTC. I'll go back and forth a bunch of times. And this monitor, this display isn't probably going to let you see all the nuances. There are some differences, but you can see it's very, very, very similar. And we have to, the reality is when we develop this codec, we do look at everything visually, but we have to be driven by the metrics back here. We're heavily metric driven. We have a bunch of different metrics. We don't just use PSNR. But anyway, going here, I want to show you the transcode. So this is the last part of my presentation. So I'm going to show you UASTC HDR versus the transcode. And this is really the new technology that I believe nobody else has done yet. You notice that the difference between the two, I don't think there is any visual difference. If there is, it's extremely minor. And so thank you very much. That's my presentation.
So if you want to use this codec, we'll be shipping in a few weeks. If you want to contribute to spec discussions, you can reach out to us directly. We also are on 3D formats calls. And yeah, there we go.